All right, we're going to look at something called Taylor and Maclaurin series in this section. If you haven't already, please watch the Khan Academy video on the intro. Mr. Khan does a way better job of explaining what these Taylor and Maclaurin series are than I could, but make sure you've watched that first. So if you haven't, pause and go back and watch that video. And what he explains in that video is we can approximate any curve with a series, an infinite series that should match, where the infinite series, if we're centering it about 0, would be the function at 0 plus its derivative at 0 times x plus its second derivative at 0 times x squared times, or divided by 2 factorial, where we got the power of 2, and that's always going, the factorial number is always going to match. Same with it matches the derivative number 2. Here we got the third derivative, x to the third over 3 factorial. And if we continue that pattern, the nth derivative at 0 would be x to the n over n factorial. And so this is a Taylor series, and when you center a Taylor series at 0, then it becomes a more specific type called a Maclaurin that we're going to be looking at today. Later we'll look at ones that are not centered at 0, so other Taylor type series. So what we're going to do is apply that now to some different functions, and the ones we're looking at today are main ones that you should know for the AP test. These are ones that you definitely want to know by heart going into that. The first one we're going to look at is what is the Taylor series and its radius of convergence for the function f of x e to the x. Okay, so what we're going to do first is we're going to take that series that we just had, that any Taylor series here can be written out as all right, so it should be written as this. Now, what we're going to do is find out what are those derivatives. So we're going to, over here, come up with a table to find those values out. So we want to know what's the nth derivative, so the different derivatives of x here, and what are those derivatives at 0. All right, so let's start with if it was just the original function f of x. So if it's just the original function, which is e to the x here, what is that at 0? So if we did this at 0, it would just be e to the 0, which is 1. If we did the first derivative, here, derivative of e to the x is e to the x. What is that first derivative at 0? Well, e to the 0 is still 1. What is the second derivative of e to the x? It still remains e to the x. What's that second derivative at 0? Again, 1, because e to the 0 is 1. And for this one, it doesn't matter how many of these derivatives we do, our derivative is always going to be e to the x, and the derivative at 0 will always be 1 here, and that'll just continue on here. So let's fill in now what this looks like. So our function p of x, then, if we replace all these derivatives, we know this is going to equal 1, this is going to equal 1, this is 1, this is 1. They're all 1 here. So if we fill those in, now we have 1 plus 1 times x, or just x, plus, now we got 1 over 2 factorial times x squared. I'm going to write that as x squared over 2 factorial. If we did the next one, that's 1 over 3 factorial times x cubed. I'm going to write that as this. And that would just continue on. The next one would be x to the 4th over 4 factorial, and so on. So what we want to look at now is what is this one going to be written as then if we keep going out indefinitely? What's another way to write e to the x? So what's our pattern here? Um, well, it looks like that it would just be x to the n divided by whatever number that power is would be the same factorial on the bottom. So e to the x, another way to write it is it's the infinite series of x to the n over n factorial. So that's another way you can write e to the n. So just summarizing that, what we know here is that we can write e to the x as the series x to the n over n factorial. That's one you need to know for the AP test. Let's take a visual of this one. In your Schoology folder, you have a link to this Desmos calculator, and it's going to be a nice way to visually see what's going on. So I'm going to open this up here, this application. You can do the same and play around with it here. First, we need to change this function to the one we're looking at. So we're going to change it to e, use your exponent caret key, so shift number 6, and then x. And then we see the graph of e to the x here. It's this blue graph right here. So when we are at 0, it would just be the tangent line, or the, not tangent line, it would just be the slope at that point, which is 1. So it's just a horizontal line at 1. If we go to the degree 1, now it's the tangent line at 1. Like you saw in the Khan Academy video. If we go another power, so now this is out to our third one, that would be, if we go back to this here, now we're doing it out to these 1, 2, 3. So now this is including the x squared term. Now it would look like this. If we go out another one, now you can see that our approximation is starting to look more and more like our blue graph there. That's pretty close around this origin right here. And that would be going out to this third term here and stopping. That would be our approximation. So it looks pretty good. Let's keep going and see how it starts getting more. So there's to the fourth. Okay, very close around 0, and now even getting out to where -2 is. And on the right side, it's pretty good out to about +2. There's the fifth one, now even really close to -2 it is. And if we just keep going, you can see it gets closer and closer to the actual thing. And right around 0, it's almost an identical match. The more we increase this, the further out the approximation really looks like the graph. So that shows you what this Taylor series is doing as a visual.